So first point, base spec. The only real substantive change in the draft 10 versus the versus RFC 1771 is that it fixes some ambiguities about MED, and in fact it doesn't change the specification, it just spells it out even more clearly. And actually that's been in the draft for a while now, so that's all I'm going to say about the base spec. We'll keep coming back to this MED point though. Okay, then the first really new thing, graceful restart, which some of you may also have heard of under the previous acronym NSF, nonstop forwarding. And this is a thing that's been introduced really for stability reasons. The idea is that when BGP is running on a router, BGP can restart without the router actually becoming totally disabled. Most modern routers have independent forwarding hardware and route computation hardware, and it's kind of silly when the route computation engine restarts or one protocol on the route computation engine restarts for your entire network to have to thrash when the forwarding hardware is perfectly capable of continuing to forward packets according to its last state. So we want to avoid route flap when there's a restart. Once that works, that should allow non-intrusive upgrades, or at least much less intrusive upgrades of routing software. It does introduce some risk, as you'll see, of transient black holes or loops, because anytime you allow two routers to get desynchronized, you have some risk of transient routing problems. But of course, route flaps, which is what we're trying to avoid, have their own quite well-known risks. So we're trading off one kind of pain for another, and we think that we're trading a little pain for a lot of pain, or vice versa, whichever one is better. The draft in a nutshell basically consists of really three things. One is a new capability that allows a router to say, "Hi, I support graceful restart," and it's got some flags. One says whether I'm currently recovering from a restart right now, and the other whether I've preserved my fib or not, because there's certainly the potential for a router that has not preserved its fib or cannot preserve its fib. For example, if the entire chassis restarted, you couldn't preserve your fib. And the other major thing that's carried by the capability is a timer, and we'll get into the timer in a second, but the idea is for the timer to say, wait this long before tearing me down if you see me restart. And the other new message that's introduced is actually kind of you could say a perversion or a clever use of an existing message, and it's a way to say this is the end of the rib, and it's used during the initial exchange of routes that we have when a BGP session is established. So it's a way for my peers to tell me I've sent you all my initial routes, and it's a way for me to tell my peers, okay, I've sent you all my initial routes, and we'll also see what that's for. So the idea is, like I said, BGP stops. The neighbors don't have to tear down the TCP session right away. They wait for the timer that I introduced in the previous slide to expire instead. And during the duration of that timer, the peers, instead of flushing the routes, since they haven't dropped the session, basically they're not going to flush the routes. They'll keep them in their rib. They'll keep using them. They'll keep forwarding as normal, and they won't propagate any route flap because, as far as they're concerned, the routes are still in the rib. They won't withdraw them. After the restarting router has come back up, it refreshes all of its routes, and any routes that aren't refreshed by the end of that phase get flushed out at that point. So at the end of the entire procedure, the network is back in sync. So, okay, I'm a little nervous. This is my first animated slide, but here's an example of the procedure. And it's important to note that this is an example. There's n different ways that, exact steps that could be taken depending on a lot of timing issues, but this should give you a flavor of how the mechanism works. So suppose on router A that BGP stops. So what happens when that takes place? In this example, I'm assuming that B and C have a way of detecting that BGP has stopped on A. For example, they might be using TCP keep lives. The other routers and the FIB on A, remember that we're assuming that A's FIB is autonomous and can continue to operate without the BGP application. They all mark the routes as stale, but they don't do anything about it yet. They just keep using them. They're marked, but they don't delete them. Okay, sometime later, hopefully a very short time later, typically we'd be hoping for a small number of seconds or less. BGP comes back up on A, and it sets up new sessions with B and C. At that point, you can drop the old sessions. And B and C send their routes to A. Now A doesn't send any routes at all to B or C until it's finished gathering routes from B, C, and any other neighbors that I haven't shown here. So A populates its RIB with all the routes from B and C, and at the end of their initial RIB update, as I mentioned earlier, B and C will each send a message that says, that's all the routes, you've got all of them now. And that's a signal to A that it can run best path. Okay, you've got all the routes, your neighbors have converged with you, and you can run best path, populate your FIB, and at that point you can advertise your new RIB out to your neighbors. The routes that, when he was done advertising A's RIB, A will also send the end of RIB message. It'll say, okay, I'm done, no more routes for me, we finished converging. At that point, the FIB and routers B and C flush out old routes, and we're done. The network is back in convergence. Just to expand a tiny bit on what I said about the possibility of transients, you could see that depending on how long the time was between BGP going down on A and BGP coming back up on A and reconverging with B and C, there could have been some changes on B and C that they would have liked to have advertised to A, but didn't have the opportunity to because BGP wasn't running at the time. If that happens, the forwarding table on router A will be somewhat out of sync with the forwarding tables in the rest of the network. We think this is a good trade-off in exchange for not flapping routes because the amount of churn that's introduced is probably fairly small in general, and the amount of churn that we're avoiding is the size of the entire routing table. Okay. The next one is route refresh. This has also been around for a while, but it doesn't seem to be in too wide use yet, which is kind of too bad. It's an extension that allows a router to send a request to its neighbor to say, send me your RIB again, please. And it's as simple as that. It's a very small little message says, send me your RIB. What benefit do we get from this? Well, it means that I can do soft reconfig, i.e. I can rerun my import policy, change and rerun my import policy, without having to have stored all of the routes locally. So without route refresh, as you probably know, if I want to rerun my import policy, either I have to restart my BGP session, why? So I can get all the routes again so I can reevaluate them, or I have to have stored all of the incoming routes. Even if my previous policy said never use this route, I still had to burn memory to store it. So there's potential to save quite a lot of memory. There are some drawbacks. One is there's extra communication. When I change my policy, I have to solicit a new RIB from the peer. And there's more CPU used on both ends to resend and reprocess the incoming RIB. This seems like a very good trade-off, though, because it's you're not going to change your policy that frequently, but on the other hand, retaining routes for soft reconfig costs you memory all the time. A related draft is cooperative route filtering. There's a base draft, which is the first one listed there, and then there's an extension for prefixes. I'm told there's another group working on an extension for AS paths, and we'll probably see more of this in the future. And this is a way to let a router, it's kind of the next step in route refresh, which is to say, okay, if I know that I'm going to filter out X, Y, and Z routes whenever you send them to me, why should you spend the CPU and why should we both spend the bandwidth for you to send these routes to me that I'm going to drop on the floor immediately? So instead, what I do is I build a filter and I send it to my neighbor. The neighbor runs filtering before sending routes to me. It's really as simple as that. You send them along with a route refresh so that if you change your policy, you kind of piggyback this whole thing together and you say, here's my new filter, send me the new routes. One other point to note is that the peer can use the outbound route filters to filter the routes. They're not required to, so this is strictly an optional thing that's a convenience for both ends if they both support it. If they don't both support it, you can still have the policy on the local end, so your filtering is still going to work the way it's supposed to. It'll just be somewhat less efficient, i.e. it'll be as efficient as it is right now. So here's a quick example. We've got a router A that's soliciting routes from router B. Router B has the forwarding table, or the routing table shown on the right-hand side. We open a session. We open the session and immediately send a refresh message saying, here's my outbound route filter. I only want to get routes with community 2. Router B only sends those routes. Sometime later, I say, oh, I changed my mind. I only want routes with community 3. Forget about community 2. Router B sends the deltas necessary for me to have the appropriate routes. That's all there is to it. Extended communities is the next one. Extended communities are very much like the communities that we know and love, only they're 8 bytes instead of 4. Any questions? Now, there's slightly more difference than that, which is that there's a type field that can be used to give structure to the other 6 bytes, and there's several different structures defined in the spec. And the interesting thing about extended communities is that there's good potential to use their structured nature to extend them a little more flexibly than communities have been used so far. Right now they're used for network-based VPNs, which I'm not going to talk about VPNs at all because that's a whole talk of its own, and it's orthogonal yet related to this one. Okay, so that covers all the new extensions that have been proposed. Now I'm going to spend a few minutes talking about updates to reflection and to confederations. So first point, reflection and confederations are actually the same thing. There's virtually no difference between them if you abstract enough and erase all the configuration commands and just look at how your routing updates flow and how they scale. So it shouldn't be surprising that the same kind of changes have been applied to both RFCs. Both of them have had editorial cleanup. The route reflection, both of them have had a deployment section update with some points regarding MED. I told you I'd get back to it. And in the case of route reflection, there's some discussion of avoidance of shooting yourself in the foot by building routing loops. In neither case has there been any fundamental change to the protocol. One further point about confederations is that there were a couple of just simple mistakes in the RFC. One was that the code points for confed sequence and confed set were reversed in the RFC versus all fielded implementations. So we just reversed them in the RFC to make them reflect reality. Also, the RFC said something about building nested confederations, and the protocol just doesn't permit it, so we removed the text. The deployment sections are really fairly similar, and I'm going to talk about them as one thing. I'm not going to try and cover them separately. All the deployment guidelines basically are driving at one simple problem, which is that both route reflectors and clusters, or I should say confederations, scale by hiding routes. Now, you get into trouble when you realize that BGP has as a basic assumption in the base spec that IBGP is ubiquitous and that all routers in the AS know about all the routes. We scale by hiding routes, so that kind of points in the direction of a possible problem. I'll go over a couple of problems that you actually can build in your network if you try hard enough. But the guidelines that are introduced in both drafts is to say you should avoid building overlapping clusters or sub-ASs, and I'll show you what I mean. And you should set your IGP metrics, if you can, to prefer intra-cluster paths over paths that cross between clusters, and we'll have an illustration of that also. So, okay, why avoid overlapping clusters? I'm not going to spend long on this because I hope this is already a famous, well-known problem. Can everyone see the green lines, by the way? Well, okay, so squint really hard, and it's probably, squinting is probably better than me trying to change the colors on the fly. Anyway, in the diagram here, green lines represent routing information. Route Reflector 1 and Route Reflector 2 are meshed together, and Route Reflector 1 has as its client Router B. Route Reflector 2 has its client Router A. So suppose both Route Reflector 1 and 2 learn about some prefix, and having, they have, for whatever reason, Route Reflector 1 elects to use the prefix that it learned from outside, and Route Reflector 2 does likewise. They pass they reflect these prefixes to their clients, just like they're supposed to, and you end up with the forwarding topology shown in red. And there's a nice simple routing loop between A and B, persistent routing loop. If you build your clusters or sub-ASs so they don't overlap the way I've shown here, this will never happen. Okay, so second point, why do we want to set IGP metrics to prefer intra-cluster paths over outside? Well, here's an example where we haven't done that. You can see that Route Reflector 2's path to reach both A and B, the numbers there on the edges represent metrics. Route Reflector 2's path is going to be 6 or 5 to reach A or B, whereas it's 10 to reach C. Okay, so what's the problem? Okay, suppose A advertises some prefix. Route Reflector 1 now has in its routing table this prefix, and it's got an IGP distance of 5 to get there. And that's all that's in there so far in the example, so it selects it. Okay, now B also advertises the same prefix. The IGP metric is a little bit better. There's an MED, but so far we don't care about the MED because these are the only two routes, and the MEDs aren't comparable because the ASs are different. Okay, so Route Reflector 1 changes to select that route because it's got a better IGP metric. Okay, now Router C also announces the same prefix to its Route Reflector. It's got an IGP of 10, but so far that's the only thing in Route Reflector 2's table. It selects it. All right, now Route Reflector 1 and Route Reflector 2 are going to exchange their routes. In some order, it's timing dependent, but this example works no matter what the timing is. Suppose Route Reflector 2 sends Route C to Route Reflector 1. Well, okay, there it is in the table. Now if you'll observe, routes B and C, remember for the same prefix, are from the same neighbor AS, and they've got different MEDs. And B has the less preferred MED, so therefore it's not eligible to be selected according to the rules in the RFC. That means that you then get down to comparing A and C, and you pick A because it's got a better IGP metric. All right, so now we send an update to Route Reflector 2 that says, oh, here's my selected route, it's A, and from Route Reflector 2's perspective, it's got an IGP metric of 6. Well, on Route Reflector 2, there's no MEDs to be compared. The IGP metric on A is better, so the selected route changes. Next step, it withdraws C because it's no longer the selected route. That takes C out of route reflector 1's table, and we run the selection process again, and we flip back to using B because it has a better IGP metric, and you should see where this is going now. We have a persistent routing oscillation, and this will go on for as long as you like. So, all you have to do to make this not happen is change the metric on your inter-cluster link so that all the metrics internal to the route reflector 2 cluster are better, and all the metrics internal to the route reflector 1 cluster are better than the intra or inter-cluster metric. And I don't have a fancy animation on this one. Just observe that you end up with route reflector 2 stably selecting C because it has actually it has both the better MED and the better IGP metric. Likewise, route reflector 1 ends up selecting A. B, as you'll recall, is eliminated because the MED is not as good, and it just sticks with A because it has the better metric. For most people, this should suffice because typically the intra-cluster links are going to be the short-haul links that you want to have better metrics on anyway. But this is a shortcoming in the protocol that I'm sure will get a lot of work in the near future. And to close, for those few of you that don't know about it, there is a mailing list for BGP. It's the IETF Interdomain Routing Working Group, and it's for discussion of the protocol. It's not for discussion of any particular vendor's implementation or how to use a feature or how to, build some particular network. I think that I can probably speak for all of the vendors certainly on that list in saying that we're very interested in hearing discussion of people's operational needs and problems with building networks using BGP on the mailing list, though. That's all. Are there any questions?
Could you discuss really briefly the how much I need to trust if I'm using outbound route filtering, how much I need to trust the other side, whether I have any indication of whether they're actually performing the filtering that they've accepted, whether I know for sure that they've accepted it, and whether if I don't assume that they've done it, if I keep the filters on my side as well, how much performance hit am I taking?
Okay, so let me see if I hit your question right. Question is, if I'm doing outbound route filtering and I've sent a filter to the peer, do I know that the peer is actually doing the filtering for me? Because then that'll let me not bother to do it on my end at all. The answer is yes, if you trust the peer's implementation. You will have exchanged a capability at the beginning when you open the BGP session. And the capability includes information about what outbound route filtering types or F types you're willing to accept and that you're willing to send. So the peer will have told you, I accept the following types of ORFs. That means that you have, I think it's reasonable to assume that you can send those ORFs to the peer and have them work. Okay. Yes.
At the recent ARIN meeting, there was an excellent presentation by Scott Marcus on the growth of AS numbers and assignment of AS numbers by the various regional registries. Given that the current AS is a 16-bit value, has there been any conversation, any discussion within the working group and to extending that, or has that been fed back into IETF as something that needs to be looked at?
There's been a little bit of discussion about it. It doesn't really seem to be a fast track kind of thing right now. There's interest in building a longer AS number.
Okay.
Respond a little bit. Sorry, let me eat the microphone. I'm Scott Marcus. I've been corresponding with Dave Oran and Bob Colton. Expectation is I will be presenting those results at the IETF in San Diego. I presume that this will probably kick off some interest. Thank you.
Thanks. Any further questions?